Assalamualaikum everyone. Okay, so for today's lesson, I will give you an example regarding the bifurcation of 1D system. Okay, so this is you are given a 1D system where there is a parameter mu. Okay, so now look at the question. Find all the equivalent points of the system. Determine the condition for each of the equivalent point to be stable if any. Okay, hence determine the bifurcation value, and then after that you have to sketch the bifurcation diagram. So these are all the things that you have to provide while you are doing the problem regarding the bifurcation of 1D system, where we have discussed in last week. Where we have done sketching the saddle knot, what else? Transcritical bifurcation, and also we have a pitchfork bifurcation. Okay, so now for today we have no idea at the moment what is the type of bifurcation that we have. Okay, so firstly you have to just like we done on the previous example, we have to look at the equivalent point for the system, but in terms of mu. Okay, so maybe this one. Okay, so we are given dx over dt given by mu x plus x plus minus x cubed. Okay, so then to get the equivalent point, so firstly we have to equate the given expression on the right by the 0. Okay, and then what we can do here, we can factor out the x. So we have mu plus 1 minus x squared equal to 0. So from here we can have x equal to 0, and also we have mu plus 1 minus x squared equal to 0. Okay, if you want to sketch your bifurcation, so you have to use this x equal to 0 and also the mu plus 1 minus x squared equal to 0, and you can sketch the bifurcation diagram. As I mentioned before, you have to have the basic of your sketching. Okay, so how can you get that? So it's supposed to be from this equation, but for that you have we have let mu equal to something in terms of x. It's more easier, but to get equivalent point you have to have x equal to, okay, because equivalent point is the value, the specific value of x, so you have to rewrite this into the x in terms of mu. Okay, so now we can, from here we can have x squared equal to mu plus 1, and we can have x is given by plus minus the square root of mu plus 1. So it looks like our equivalent points, there are 3, where we have x equal to 0, and we have x equal to positive square root of mu plus 1, and we have x equal to negative square root of mu plus 1. Okay, so now we want to investigate the how many equivalent points that we have for some specific mu. Okay, so now we work on it. So last time what we have done, we analyze the stability for the equivalent point for mu positive, mu negative, and mu equal to 0. But it depends on the equivalent point that you have. It's not necessarily you have the positive, negative, and equal to 0. It depends on your information provided here, where you have already obtained. You can see here the number of equivalent point depends on the value in the square root, right, which is coming from mu plus 1. Okay, so you can see here, if mu plus 1 is positive, right? If these are all positive, meaning that you can have 3 equilibrium point, which is a real number, 0 and whatever value, mu plus 1. Okay, because mu plus 1 is positive, and you will let's say you got 2. Let's say that you got the square root 4, you got 2, and this one you got minus 2. But now, how about the number of equilibrium point if our mu plus 1 is negative? So meaning that the total number of equilibrium point depends on the mu plus 1, not mu. Okay, so in this case, what we can do here, just look at on the this one and this one. So we have mu plus 1 whether it is negative or positive. Okay, so now if you have this one, where what we can do here, what we can have here is you have mu less than negative 1. Okay, and this one you can have mu greater than minus 1. Okay, so meaning that now the domain, I mean the range for mu, it should be greater than 1, minus 1, and smaller than minus 1. And then we want to also analyze the stability at the equilibrium point when mu is equal to minus 1. Okay, so it's just like when you draw a line number. So you have this one is the value of mu. Okay, and then you want to know what happened to the system if the mu is greater than minus 1, which is around here, and your mu is smaller than minus 1, which is around here, and also exactly at minus 1. So then from there we can sketch a diagram. Understand? Okay, so firstly, the first case, we want to have if our mu is less than minus 1. Okay, so now look at our equilibrium point. So mu less than minus 1, which is coming from this one, which is mu plus 1 is negative. So if this one negative or this one negative, they will get a imaginary number which is not real. So meaning that for this, our equilibrium point is just x equal to 0. Okay, so whether you can have fixed point or equilibrium point, so it's up to you. So our fixed point or equilibrium point is just x equal to 0. Okay, now you have to have use the theorem to determine the stability at the equilibrium point, where you have to remember last time we assume this one is the function of x given by mu x plus x minus x cubed. Okay, and then we using the theorem to determine the stability for 1D system, we can differentiate that respect to x. So you got mu plus 1 minus 3x squared. Okay, so it looks like we can use this. Okay, we can use this to determine the stability. Suppose we have x squared here. Okay, mu plus 1 minus x squared. Okay, so then we replace f prime mu, we have something in terms of mu, and x is equal to 0. So what's the answer? So we got mu plus 1. Okay, so in this case, our f prime when x equal to 0. So as we know that this one is coming from here, which is mu plus 1 is negative. So mu plus 1 is negative. So it's supposed to be this one. So we can say that this one is stable. Okay, so it looks like it is stable. Okay, we can see that when mu is smaller than minus 1 around here, so we only have a single equilibrium point, x equal to 0, and it is stable. Okay, and then The other one, mu greater than minus 1. Okay, mu greater than minus 1, which is coming from this one. Mu plus 1 is positive. So how many equilibrium points that we have? We got 3, right? And because mu plus 1 is positive, and then this will give you a real number. Okay, so you got 0, and they are all the equilibrium point. So for this, the fixed point, there are 3, x equal to 0, and then x equal to plus minus the square root of mu plus 1. So here we want to investigate the stability for mu greater than minus 1 at each of the equilibrium point. Okay, so when x equal to 0, so f prime mu 0. Okay, and we replace here and we set for 0. So we got mu plus 1. And in this case, mu plus 1 is positive. Okay, so we can say that when mu greater than minus 1 at x equal to 0, it is unstable. Okay, and then we go to the next at x equal to positive mu plus 1. So we replace positive square root mu plus 1. And then we substitute into the f prime. So mu plus 1 minus 3 our x squared, so mu plus 1. So mu plus 1 minus 3 mu minus 3. So we got negative 2 mu minus 2, isn't it? So we can have minus 2 mu plus 1. Okay, so in this case, this is for the case of mu plus 1 positive. So this one positive. So this one positive. So meaning that all the values here should be negative. So it tells you that at this equilibrium point, when mu is greater than minus 1, it is stable. Okay, and then we figure out for the third one, at x equal to negative square root mu plus 1. Okay, and then we plug into the f prime. So now we have negative square root. So we substitute into our f prime. So you got mu plus 1 minus 3. So now our x squared, so the negative gone. So you got mu plus 1. Okay, and we simplify with mu plus 1 minus 3 mu minus 3. And when we simplify that, we will get the same. So you got negative 2 mu minus 2, which is minus 2 mu plus 1. And this one also stable. Okay. Okay, so we done investigating this range and this range. Now we want to know what happened to the system if mu is exactly equal to minus 1. Okay, which is now we go to the third case. So this is the first case and this is the second case. Now we go to the third case where mu is equal to 1. So when mu equal to 1, so we substitute into our system up here. Okay, so you just set mu is equal to 1. Okay, and then and also we look at the equilibrium point. So imagine that when mu is equal to negative 1, not 1, sorry, minus 1. So this one 0 and this also 0. So the total equilibrium point is only 1, which is x equal to 0. Sorry, this one is supposed to be -1. So our fixed point is only x equal to 0. Okay, so now we want to investigate for this mu -1 exactly at -1 and x equal to 0. So our f prime, so our mu is now -1 at x equal to 0. So we substitute into the f prime. Where is it? Okay, this one. Substitute here. So we substitute mu is -1, so -1 plus 1 and then -3 and then 0. So we got equal to 0, which telling you that the test failed. Okay, so we can it is inconclusive. You cannot have you cannot have any conclusion. Okay, but remember you can use the function or the graph here, the original graph. But you have to substitute. So this is the original, but you have to substitute that the mu is equal to 1. Okay. Okay, so when you substitute mu equal to -1 into your system, we'll get this one. This is after you replace mu by -1, so this one eliminated, so you only have -x cubed. So next we're going to look at the phase line. Okay, so because using the formula or the theorem is failed, so we have to use the phase line. Okay, so now we have to provide the phase line where this is the function of x in terms of x, so you got -x squared. Okay, so this is your function now after you replace mu equal to -1, and then we look at the phase line. So the fixed point is at x equal to 0. So now we look at the value of x dot y x dot for some specific values of x. So we put choose the value in this range. So I put -1 and also +1. So when you substitute, you have a -1 cube and negative gone, so you got positive. And now when your x is 1, so this becomes -1, so got negative. So when it is at -1, so you are turn right, and then when at x equal to 1 is turn left. So it looks like when mu is exactly at -1 and the fixed point x equal to 0 is a stable. Okay, so next we have to we done all, we check all of them. So now we want to obtain the bifurcation diagram. Everything, so we draw them, which is you go to the next question. So sketch the bifurcation diagram for the mu x plane. Okay, mu x plane. Okay, so now to sketch the bifurcation diagram, you have to look at, again, I mentioned just now, you have to look at from your how you get the equilibrium point. So look at this equation. So you have to have x equal to 0, and you have to have this one. Okay, so now we sketch the diagram. Okay, so just now this is y-x. So just now you have the line of x equal to 0. Okay, so I forgot this one. It's not y-x but x mu. This is a bifurcation diagram. Okay, so x versus mu. Okay, so you have the line of x equal to 0, and also one of you have mu plus 1 minus x squared equal to 0. So x equal to 0, where is the line? So this is the line. Okay, and how about the second one? The second one here, remember, so this one we assume this to be x and this one to be y. So just if you forgot the shape, okay, so now we try to just look at the original one, mu plus 1. So you have from here you have mu equal to x square minus 1, or if you use a y-x plane, so you have you can imagine this one is equivalent to x equal to y square minus 1. So about the shape of this particular graph, y versus x. Okay, you have the quadratic, yes, but then the square is on y, not x, so it looks like you have a C shape. Okay, C shape. So your graph is something like this, and you have a negative 1 here, so it should be symmetry, something like this. Okay, so you got that. So that is your bifurcation diagram, plus x equal to 0. So you draw it. So I put in the red color, so maybe like this. Okay, and this one is minus 1. Okay, so this one is on the x mu diagram. Okay, so now, so you are getting there, but then you have to look at your result then. Okay, just now we said that the first case. Okay, so you have to provide the dash line and also the solid line, which telling you which one stable and which one unstable. Okay, when mu negative, less than negative 1. So you got only single fixed point x0 and x0 is stable. So from there, okay, I put the tebal sikit So x0 here. So for this area, for this region, when mu less than minus 1, so this one should be solid line, telling you that this one is stable. Okay, and then we go to the mu greater than minus 1. We got 3 equilibrium points. So x0, you still have the same line as the previous one, but when mu greater than minus 1, it is unstable, which is based on this line. This line is telling you x equal to 0, right? So after you passing through mu equal to minus 1, so it becomes unstable. So you have to provide the dash line. Okay, dash line. So dash line. Okay, what else? So we go to the okay. Now the positive square root and the negative square root, where these two expression coming from? It's coming from the, okay, look at again here. This positive plus minus positive plus minus square root is coming from the quadratic, right? But now x in terms of mu. Okay, x in terms of mu, meaning that graph dia sama lah. Graf dia samalah dengan kuadratik yang ini. Bezanya yang ini you buat mu sama dengan x squared minus 1. Tapi yang tadi x sama dengan, sebab tu ada punca kuasa. Then graf dia sama, cuma representation sahaja berbeza. So meaning that you have obtained when mu greater than minus 1, so dekat area region ni, kat kawasan ini, that quadratic, they are all stable. Macam mana tahu? You have investigate that just now. So positive square root maknanya x yang belah atas positif. So it is stable, and x belah bawah, which is x negative kat bawah, also stable. So for this, you have to provide a solid line. Okay. So dah belum. Okay, ada lagi satu. One more. Exactly at mu minus 1. So you have shown that you only betul-betul dekat mu sama dengan plus 1, you ada just single x0, which is we can see from here. This one. So this one, x equal to 0. So this one is actually minus 1. This one. Okay, this point is minus. And it is stable. So meaning that dekat situ termasuklah solid line sebab dia stable. Okay, tapi just after mu, katalah negative negative 1.1, negative 0.995. Okay, so start from when mu is greater than -1, which is contoh, for example, mu is at negative 0.995, for example, and your system turn out to be unstable at this equilibrium point, at this line. Okay, so now, so we done that, but then look at here. So look at here, sketch the bifurcation diagram. Okay, so before you proceed to the next question, you have to read whether you already obtain all the question or all the requirements. So first find all the equilibrium points. So you done that, right? So you done that. You got this one. You got this one. Okay. Determine the condition for each of the equilibrium to be stable, if any. So you done that. Hence, determine the bifurcation value. Okay. So you haven't done determine the bifurcation value. Bifurcation value apa dia? Ingat tak saya sebut sebelum ni? The point that you start to bifurcate. Point pada X dengan mu bila sistem awak start berubah stability dia. So kalau you tengok kat sini, asalnya sistem tu kalau dekat region ini, which is mu less than -1, so dia stabil. And cuma ada satu saja equilibrium point dia, satu saja. But then bila dia mencecah kepada mu yang lebih besar daripada negatif 1, so sistem tu dah berubah stability dia. Daripada satu equilibrium point jadi 3 equilibrium point, di mana satu unstable and the other two are stable. Okay, macam mana you baca tu? Okay, macam saya sebut sebelum ni. You just imagine, I draw a line. Okay, I draw a line. Okay, so that one is, let's say dekat mu sama dengan, hopefully you boleh nampak tu. Let's change the color. So let's say this one is mu minus 2. When mu is -2, so you masukkan mu -2 in the system. Okay, lepas tu you buatlah phase line dia. You cari equilibrium point dia. Macam biasa. Okay, and you will obtain that there is only fixed point which is x equal to 0 and it is stable. Maknanya kalau you ubah banyak-banyak kali, tak payah you nak buat ubah setiap kali. Katalah saya minta, okay, what is the stability of the system if mu is -4? And then after that, I ask you again, when mu is -3. Takkan every time you nak ubah, you nak buat balik benda yang sama. So it is wasting your time. So we just use the bifurcation diagram and you can see without repeating all the process, without wasting your time, we can determine the stability for different value of mu on this region. Okay, but then after mu greater than, when mu is passing through the -1, so let's say now I give another line, which is now we got here, or you got here. Okay, so then what happened to your system? What in terms of stability? So you can see that from the diagram without recalculate everything, all the steps. So you can determine when mu is greater than -1, for example, you got here is mu is negative 0.95, for example. Okay, and you obtain that the system. So you masukkanlah dalam ni, you masukkan dalam ni inside here, and then you will have the negative 0.59x and so on, and then you buat dia punya phase line. And then you can you can see that there are 3 equilibrium points, which is this one, this one, this one, and this one. And you can determine that the two here, which is positive square root and negative square root, they are stable. But x equal to 0 is unstable. So this behavior will be the same for any mu as long as they are in this region, in this category, which is mu greater than -1. Understand? Okay. So now we go back to the bifurcation value. So from here, the bifurcation value is apa dia? X naught mu naught, right? X naught mu naught is given by, kat mana? Kat mana start berlakunya bifurcation? Dekat point ni lah. Which is, X naught is 0 and mu naught is minus 1. Okay, X naught mu naught. The value of mu at which the bifurcation occur. Okay, so then sketch the bifurcation. Then you done that. Okay, and then state the type of bifurcation. Okay, tell me. You got 3 types of bifurcation that we have done discussed. We have discussed before this. So we got saddle knot. Okay, where saddle knot and pitchfork. Remember pitchfork bentuk dia macam apa? Macam penggarut sampah tu. Saya tunjukkan gambar dia kan. And the other one is transcritical. So you can see that this one is pitchfork bifurcation. Okay, so here to answer that, so we got the pitchfork bifurcation. Okay. So the pitchfork bifurcation, okay, maybe if you want to explain, so pitchfork bifurcation occurs at mu is minus 1 and x equal to 0. That is bifurcation value. So why that is the bifurcation value? So because pitchfork bifurcation occur okay. So x equal to 0, which is the fixed point of x equal to 0, lost its stability as mu increase. And another, this is the physical description, and another 2 fixed point appear, and these are stable as mu increase from mu minus 1. So this is the physical description, just for your understanding. Okay, but if you want to answer this question, so just enough for you to provide me the diagram and also the bifurcation value, unless they ask you, maybe they will ask you, give the reason why the bifurcation value occurs and x naught 0 and mu naught minus 1. So this is the reason. Okay, so you can see that at x equal to 0, as I mentioned before, it lost the stability from stable to unstable when mu increasing. But then at the same time, the 2 equilibrium point or fixed point appear. Okay, and these are stable. So these are the description of the pitchfork bifurcation. Okay, so hopefully you understand that. Okay.